Hello and welcome to Algebra 2, Lesson 67. In this lesson, we're going to learn about quadratic and rational inequalities. So we're going to start out by talking about quadratic inequalities. And a quadratic inequality is of the form, you'll see ax squared plus bx plus c is greater than 0. And of course, we have the restriction that a is not equal to 0. But other than that, a, b, and c can be any real number that you choose. Of course, when we see something generically, we have to choose something to go there. So here we have a greater than, but of course the greater than can be a less than or equal to, or a greater than or equal to. So before we jump into how to solve a quadratic inequality, I just want you to think back for a moment to when we solved a linear inequality in two variables. The very first thing we did was to replace the inequality symbol with an equal symbol. That gave us a linear equation in two variables, and we were able to graph the resulting line. Now that line had a special name. It was called the boundary line. And what's important about the boundary line is it separates the coordinate plane into two regions. One region would be the solution region. So everything in that region satisfied the inequality. The other side of the boundary line would be the non-solution region. So everything on that side would not satisfy the inequality. So from understanding that, we come up with this idea of a test point. I can figure out where the solution region is by grabbing a point on either side of that boundary line, plugging into the original inequality, and seeing if I get a true statement. If I get a true statement, that means my test point is in the solution region. If I get a false statement, that means my test point is not in the solution region, and the other region on the other side of that boundary line is going to be the solution region. Now, another important thing to kind of note here before we move into this process, the boundary line, remember, was part of your solution if you had a non-strict inequality, and it was not part of your solution if you had a strict inequality. You're going to see that thinking about that process just for a minute is going to bring back some things that are going to help you get through this here. All right, so when we're solving a quadratic inequality, the very first thing you're going to do is you're going to write the inequality as an equation, and you're going to solve that equation. So this is going to give you a quadratic equation, and you can just use the quadratic formula, or in some easier examples, you'll be able to factor this guy and just use your zero product property. So once you've obtained the solutions from your quadratic equation, these solutions will be used on a number line. So this is going to be an old-fashioned number line, one you learned back in pre-algebra, and essentially, this is going to tell us what the boundary points are, or the endpoints. So these will be the points that separate the solution region from the non-solution region. So essentially, these solutions will set up intervals on the number line. And you'll see this in a minute when we get to an example. Essentially, in each interval, you can grab a test point, okay? So we substitute a test point from each interval into the original inequality. So obviously, if the test point is successful, meaning it satisfies the inequality, that interval is part of the solution set. If it fails, if it produces a false result, then that interval is not part of the solution set. All right, now lastly, the endpoints, or the boundary points, however you want to call it, they are included in the solution set for a non-strict. So you have a greater than or equal to, or less than or equal to inequality, and excluded for a strict inequality. So if you have strictly less than or strictly greater than, they're going to be excluded from the solution. Okay, so now let's jump in and just look at a problem. Once we kind of get going on these, you'll see that they're very, very easy to solve. So we have 3x squared minus 10x plus 3 is greater than 0. So the very first thing I want to do is I want to make this into an equation. So 3x squared minus 10x plus 3 is equal to 0. Okay, so I know that this is a quadratic equation. I can use my quadratic formula to solve this pretty easily. I just want the values for a, b, and c. So a is 3, b is negative 10, and c is 3. So we could say that x is equal to negative b. Here b is negative 10. So the negative of negative 10 is 10, plus or minus the square root of b squared. Negative 10 squared is 100. And then you have minus 4 times a times c. A is 3, c is 3. So you say 3 times 3 is 9, so 4 times 9. All right, so 4 times 9 is 36. If I had 100 minus 36, that would be 64. So this would be 64 here, and this is all over 2a. A here is 3, so this is all over 6. Square root of 64 is 8. So this sets up two scenarios for us. We'll have x is equal to 10 plus 8, which is 18 over 6, so that's going to be x equals 3. Or 10 minus 8, which is 2 over 6. 2 over 6 would reduce to 1/3. So x equals 1/3. All right, so now we want to take these guys and bring them down to the number line. All right, so we're just going to paste the answers here. So we have x equals 3 or x equals 1/3. So the whole idea here is that those answers are going to set up intervals for us. So at x equals 3, that's going to be an endpoint. So I can kind of circle 3, and you can draw just a little vertical line going down. And then at x equals 1/3, you do the same. So I don't have a notch for 1/3. I'd say it'd be about right there. It doesn't need to be precise. You're just doing this for a visual representation. So I can just kind of draw a vertical line there. And essentially, you now have 3 intervals here. So you have anything left of 1/3. So let's just call that interval A, just for talking, okay? Then you have anything greater than 1/3 but less than 3. Let's call that interval B. Then you have anything that's greater than 3, okay? Anything greater than 3. So that's interval C. So now that I have these intervals set up, I can just grab test points from each interval, see if they work. If they do work, that interval is in the solution set. If they don't work, the interval is not in the solution set. So from interval A, the easiest number to grab would be 0. So I'm going to go back up to my original inequality, and I'm going to plug in a 0 for x. So a 0 there and there. What would happen? Well, this is going to cancel. This is going to cancel. I'll have 3 is greater than 0. So we know that's going to work. So anything to the left of 1/3 works as a solution. So I'll just write that this is true. Okay, this is true. Any value you plug in there would work. So what about this region where we have the capital letter B? So I can just choose something like 1. Okay, 1 is in that interval. And if I plugged in a 1 for x, what would I get? So 1 squared is 1. 3 times 1 is 3. Minus 10 times 1 is 10. Plus 3 is greater than 0. 3 minus 10 is -7. -7 plus 3 is -4. Is -4 greater than 0? No, it is not. So that produces a false result. And so the values in this interval, we'll call it interval B again, do not satisfy the inequality. And so it's not going to be part of the solution set. So I'll write false here. False. Then what about interval C? Well, this is anything greater than 3. So I could just choose 4. And we'll go back here and just plug in a 4 for every x. So 4 squared is 16. 3 times 16 is 48. Minus 10 times 4 is 40. Plus 3 is greater than 0. So 48 minus 40 is 8. 8 plus 3 is 11. 11 is greater than 0. So this results in a true statement. So we can go ahead and say that this is true over here. Okay, so let's erase this. We don't need this information anymore. So all I'm going to do is write my solution. And I can think about this graphically. I can think about it in interval notation. I can also think about it using set builder notation. There's just lots and lots of ways to write the solution. Graphically, I know that 1/3 and 3 are not included. If I go back up, I have a strict inequality. So that means my endpoints will not be included. So I would put a parenthesis at 1/3 facing to the left, and I would shade everything to the left to indicate that, hey, 1/3 doesn't work, but anything to the left of 1/3 would work. Then at 3, I'm going to put a parenthesis facing to the right, and then I'm going to shade everything to the right. So 3 doesn't work, but anything to the right of 3 would. Now that's the graphical solution. We saw that before, back when we started solving a linear inequality in one variable, right? We've been doing this forever. And another thing we can do, we could use set builder notation. So we could say the set of all x such that, we just list the conditions. So one condition is that x is less than 1/3, then or The other condition would be x is greater than 3. So any value we choose for x that's less than 1/3 or greater than 3 will work as a solution in this inequality. Then another thing we can do interval notation. So from negative infinity up to but not including 1/3. It's this set, and it's going to be the union with the other set, which is not including 3, but anything larger. So before we kind of move on to the next problem, I want to demonstrate how you could go about solving this graphically. The first thing you would think about is you would think about just f of x or y is equal to 3x squared minus 10x plus 3. Say, okay, this produces this parabola right here. I would replace f of x with 0, and I would solve. We know the solutions are x equals 3 or x equals 1/3. So that gives me an x-intercept that is 3, 0, which is right here. And it gives me another x-intercept, which is 1/3, 0, which is right here. So again, these x-intercepts will represent boundary points or places where you go from a solution region to a non-solution region, right? It's separating the two. Now, let me just scooch this down a little bit. Let me scooch this down. Let me just say this is now greater than 0. So what am I asking for in this problem graphically? I'm just asking for what x values make y or f of x greater than 0. Well, I can easily see that starting at 3, but not 3, right? Because an x value of 3 gives me a y value of 0, and 0 is not included because it's a strict inequality. But anything to the right of 3 going this way, as we move this way, we can see that the y values are larger than 0. It's the same thing over here. 1/3 is not included because it makes y 0, and again, we have a strict inequality. But anything going to the left, right, as x gets smaller than 1/3, that's also going to give me a y value that's greater than 0. So this is a method you could theoretically use to solve this guy. I think it gives you a good insight to look at it a few times, but it's just not very practical, right? If you had to take out graph paper and graph this guy and like set up a parabola, it's just a lot of extra work, right? Maybe if you're using a graphing calculator, maybe if you're using software, it could be easier for you. But I think the method that we just used is much preferable to graphing. All right, let's take a look at one more of these. So we have negative 2x squared minus 5x plus 96 is greater than negative 9x. Of course, we want to add 9x to both sides of the inequality. That'll cancel. You'll have negative 2x squared. Negative 5x plus 9x is positive 4x. And then plus 96, and this is greater than 0. Now, if you want to make the numbers you're working with a little bit smaller, we can divide both sides of the inequality by 2 or negative 2. But if we're dividing by negative 2, remember, we have to flip the direction of the inequality symbol. So this would now be a less than. So this would be x squared minus 2x, so minus 2x. And then 96 over negative 2 is 48, so minus 48. And this is now less than 0 over negative 2, which is 0. All right, so this is going to be the inequality we're working with here. And I'm just going to change this into an equation. So I'll change this into x squared minus 2x minus 48 is equal to 0. I can easily solve this using factoring, or you can use the quadratic formula. It doesn't really matter. Let's just go ahead and use the quadratic formula so that we're consistent. So x equals negative b. In this case, b is negative 2. So the negative of negative 2 is positive 2, plus or minus the square root of b squared. Negative 2 squared is 4, minus 4 times a is 1 here, so times 1, times c is negative 48. Okay, this is all over 2a. A is 1, so just over 2. So the easiest way to do this is just think about this as plus negative 4 here. So negative 4 times negative 48 is 192. So you would have 4 plus 192, which is 196. And the square root of 196 is 14. So this would be 14 here. So my two solutions would be x is equal to 2 plus 14 is 16. 16 divided by 2 is 8. Or x is equal to 2 minus 14 is negative 12. Negative 12 divided by 2 is negative 6. So x either equals 8 or x equals negative 6. Okay, so let's take this down to the number line. Okay, so we have x equals 8. So 8 is right here. And then x equals negative 6, so that's right here. So again, just draw yourself a little vertical line at each endpoint. And you're dividing the number line into regions. So left of negative 6, we'll call that region A or interval A. Between negative 6 and 8, we'll call that interval B. And then to the right of 8, we'll call that interval C. So in interval A, let's just pick negative 7. So does negative 7 work as a solution? So plug in a negative 7 here and here. Negative 7 squared is 49. Then you'd have negative 2 times negative 7, which is plus 14, and then minus 48. So is this less than 0? We know without even doing the problem it's not. 49 minus 48 would be 1. 1 plus 14 is 15. So we know that 15 is not less than 0. So that's false. So we can say this is false. Then what can we say about this interval or region B? We can just choose 0. And if we plugged in a 0 for x, we know that this would go away. You'd have negative 48 is less than 0. That's true. So this is true. And then for region C, we could just choose 9. So if I plugged in a 9 for x, 9 squared is 81. Then negative 2 times 9 would be minus 18, and then minus 48, and this is less than 0. 81 minus 18 is 63. 63 minus 48 is 15, so 15 again is not less than 0. So anything in region C would fail, so this is false. Now you're working with a strict inequality here, so your endpoints or your boundary points are not going to be included. So graphically, I would put a parenthesis at negative 6 facing to the right, and a parenthesis at 8 facing to the left, and I would just shade everything in between. So anything larger than negative 6 up to but not including 8 would work as a solution for that inequality. So in set builder notation, we could say the set of all x such that x is greater than negative 6 and less than 8. And then to kind of wrap this up, I'm just going to use interval notation. I'm going to have a parenthesis, negative 6, and then up to but not including 8, so another parenthesis. So this is my interval. Again, anything larger than negative 6, up to but not including 8. All right, so now let's talk a little bit about how to solve a rational inequality. So with a rational inequality, you're really just thinking about the exception here where the denominator is made into 0. Remember, we can never divide by 0. So that's the one thing that you really got to pay attention to here. Everything else is pretty similar. So the first thing is to write the inequality such that 0 is on one side and a single fraction is on the other. Then once you've done that, you're going to find all values that make the numerator or denominator 0. So I'll take the numerator, I'll set it equal to 0, and I'll solve it. I'll take the denominator, I'll set it equal to 0, and I'll solve it. Now, any value that creates a 0 denominator is excluded from the solution set. Excluded from the solution set. In the case where you have a value that makes the numerator equal to 0, you've got an endpoint there, so you've got to pay attention to whether it's a strict inequality or a non-strict inequality. All right, so again, we're using the solutions that we got, or the values, to create intervals on the number line. Again, these are going to be our endpoints or our boundary points. And we're just going to test a number from each interval to determine the solution set. So very similar to what we just did. Again, we just have to remember that we can't divide by 0. So as a last point, we have here that endpoints are included when they do not make the denominator 0. And we have a non-strict inequality. So if you have a strict inequality, they're never included. If you have a non-strict inequality, they're included only in the circumstance that they do not make the denominator 0. If you put something in there that makes the denominator 0, you're going to get the wrong answer. Okay, it's a common mistake because you go from quadratic inequalities to rational inequalities in the same section. You get used to, oh, I have a non-strict inequality, so I throw it in my answer, and then it's wrong. All right, let's look at the first example. So we have x plus 1 over x plus 3, and this is greater than 5. So the very first thing I'm going to do, I'm going to subtract 5 away from each side of the inequality. So I will have x plus 1 over x plus 3 and this is minus 5, and this is greater than 0 now. So how do I write this as a single fraction? Well, I just need to get a common denominator going. So let me kind of move this down a little bit. Let me kind of scooch down, get some room going. To get a common denominator, I would just multiply this by the quantity x plus 3 over the quantity x plus 3. Very easy. So I would have x plus 1, and then negative 5 times x would be minus 5x, and then negative 5 times 3 would be minus 15. This is over the common denominator of x plus 3. Of course, this is greater than 0. So in the numerator, if we combine like terms, x minus 5x is negative 4x, and then 1 minus 15 is negative 14. So you would have negative 4x minus 14, and this is over x plus 3. And again, this is greater than 0. Now, what I want to do, I want to take the numerator, and I want to set it equal to 0. So negative 4x minus 14 is equal to 0. Okay, so I would just add 14 to each side of the equation here. That's gone. I'll have negative 4x is equal to 14. Divide both sides by negative 4. That'll cancel with that. I'll have x is equal to. We know this would be negative. 14 is divisible by 2, and so is 4. So 14 divided by 2 is 7. 4 divided by 2 is 2. So this would be negative 7 halves. So x equals negative 7 halves. That's going to be one endpoint, and that's going to be from the numerator. So the other endpoint is going to come from setting x plus 3 equal to 0. In this case, I could just subtract 3 away from each side of the equation. I get x equals negative 3. So x equals negative 3. This comes from the denominator. Now, in this case, I have a strict inequality, so neither endpoint will be a solution. But in the case where it's a non-strict inequality, I can take negative 7 halves and it would be a solution, right? Because you think about the fact that if this was a greater than or equal to, if I plugged in a negative 7 halves for x, the top part would become 0. 0 divided by anything other than 0 would give me 0. So I would get 0 is greater than or equal to 0, which would be true, right? 0 equals 0. But because I pull this away and make this a strict inequality, this will not satisfy the inequality, so it's not part of the solution set. The x equals negative 3 will never be part of the solution set, because if I plug in a negative 3 down here, I get negative 3 plus 3, which is 0, and I cannot divide by 0. So it's very important that you pay attention to what's going on. I always tell my students to label where everything came from so you don't forget. So let's copy this. And so these are going to be my endpoints. So negative 3 is right here. Let's make a little vertical line there. And negative 7 halves, where's that going to be? Well, it's negative 3.5 really if we thought about it. So it's about halfway between negative 3 and negative 4. So let's say it's about right there. Let's say this is negative 7 halves. Let's make another vertical line there. So it's going to set up a kind of small region. Let's say this is region A, this is B, and this is C. So in region A, let's pick something easy. Let's just take negative 5. So I'm going to plug back in for x in the original inequality. So I'm going to plug in a negative 5 there and there. So negative 5 plus 1 is negative 4. So you'd have negative 4 over. Negative 5 plus 3 is negative 2. So this is supposed to be greater than 5. Negative 4 divided by negative 2 is positive 2. So is 2 greater than 5? No. So this would be false. This is false. We can say this one was false. Okay, so it's a pretty narrow region where we have between negative 3 and basically negative 3.5. But we can use negative 3.25 because that would lie between those two. So let's go back up and let's say we have negative 3.25. So negative 3.25. So negative 3.25 plus 1 would be negative 2.25. Then this is over. Negative 3.25 plus 3 would be negative 0.25. If I divided negative 2.25 by negative 0.25, I would get 9. So this would be 9 is greater than 5, which is true. So for region B, I could say this is true. Then for region C, let's just pick 0. If I plugged in a 0 for x, what would I get? So So 0 there and a 0 there. Essentially, these are gone. You'd have 1/3, right? You have 1/3, which is not greater than 5, so that's false. So this is going to be false. And so we're ready to give our solution. We know that the endpoints, -7/2 and -3, are not included. So essentially, all we would have here is we would graph a parenthesis here at -3.5 or -7/2 facing to the right, and a parenthesis here at -3 facing to the left, and then we would just graph everything in between. So that's your graphical solution. I can erase the false and true and the A and the B and the C. Don't need any of that anymore. And we can say that in solution set notation, we can say the set of all x such that x is greater than -7/2 and x is less than -3. And then lastly, if we were to use interval notation, put a parenthesis, -7/2, comma, you would have -3, and then a parenthesis. All right, pretty easy overall. Let's just look at one more to kind of wrap things up. We have x minus 2 over x plus 2, and this is less than or equal to 2. So again, I want one single fraction on one side, and then I want 0 on the other. So I'm going to add -2 to both sides, or subtract 2 away, however you want to think about that. So I would have x minus 2 over x plus 2, then minus 2, or I could put plus -2, again, however you want to think about that. And this is less than or equal to 0. So to get a common denominator, I'll multiply this by the quantity x plus 2 over x plus 2. And what that's going to give me, I'll have x minus 2, and then -2 times x, so minus 2x, and then -2 times 2, so minus 4, over the common denominator of x plus 2, and this is less than or equal to 0. So x minus 2x is -x, and then -2 minus 4 is -6. So you have -x minus 6. -x minus 6. This is over x plus 2, and this is less than or equal to 0. Okay, so pretty easy to get to that point. And then again, all I want to do, I want to take my numerator, which in this case is -x minus 6, set it equal to 0. I could solve this by adding 6 to each side of the equation. That would go away. I'd have -x is equal to 6. Multiply both sides by -1. You get x is equal to -6. So for the numerator, x is equal to -6. Okay. For the denominator, we have x plus 2. So x plus 2 is equal to 0. Subtract 2 away from each side of the equation. You get x equals -2. So for the denominator, x equals -2. So in this case, we have a non-strict inequality. You have less than or equal to. If I use x equals -6, plug in a -6 here. So you get -6 minus 2. That's going to give you -8. So you'd have -8 over. You'd have -6 plus 2, which would give me -4. This is less than or equal to 2. -8 over -4 is 2. So what you end up with here is a true statement. 2 does equal 2. So this part right here, x equals -6, this is going to work out for us. What's not going to work out for us is the denominator part where it says x equals -2. This will not be a solution. If I plug in a -2 for x, I'm going to get a 0 denominator. So you've got to pay attention to those endpoints you get. One's going to work here, one's going to not. So let's get this down there. So again, x equals -6, that's going to be right here. And I'll draw a little vertical line for myself. And then x equals -2 is right here. I'll draw a little vertical line for myself there. So let's call this region A. Let's call this region B. Let's call this region C. So in region A, we can just choose -7. So let's erase this. And if I plugged in a -7 here and here, what would happen? -7 minus 2 is -9. -7 plus 2 is -5. -9 over -5 is 9/5. So 9/5. Is this less than or equal to 2? Well, yes, it is. I would need a numerator of 10 to produce a result of 2, right? 9 divided by 5 is going to be less than 2. So this satisfies the inequality. We could say this is true. So anything in region A is true. What about region B? We could choose something like -4. So for -4, if I had -4 minus 2, I get -6. If I had -4 plus 2, I get -2. -6 divided by -2 is +3. So you'd have 3 is less than or equal to 2. That's false. 3 is not equal to 2, and 3 is not less than 2. So that does not work. So anything in region B is going to be false. Then for region C, I can choose 0. So if I plugged in a 0 for x, I would basically have -2 over +2, which would be -1. And we would say -1 is less than or equal to 2. That's true. So for region C, we would say this is true. Now again, when we think about our solution, the x equals -6, the one that came from our numerator, is going to be part of our solution. So let me erase all this, and I'll say x equals -6 is part of the solution. So I'll put a bracket there, and then anything to the left of that is going to work. Right? Anything to the left. Now at x equals -2, -2 is not going to be part of the solution, right? That made the denominator 0. So I'm going to put a parenthesis there, and then I'm going to shade everything to the right. Right? So anything that is -6 or less, and then also anything larger than -2 would work as a solution here. Let's erase this. In solution set notation, we'll say the set of all x such that x is less than or equal to -6, or x is greater than -2. And then an interval notation coming from -infinity up to and including -6. So you get a bracket there, and then the union with, we'll have a parenthesis here because -2 is not included, out to +infinity.